2-point charges are located on the x-axis. One of 4 nanocoulombs is located at the origin, and the second of 6 nanocoulombs is located at the point 0, 15. What is the electrical potential energy associated with the arrangement of charges if a third charge of -5 nanocoulombs is at the point 30, 0? Draw the x-axis here. One of the points is at the origin, so we've got the y-axis. So the first point is at the origin, and it is 4 nanocoulombs. I'm going to call that Q4. A second of 6 nanocoulombs is at 15 centimeters. So over 15 up 0, so we're right about here, and that is a charge of 6 nanocoulombs, so we'll call it Q6. And then we add a third charge, and that is at over 30 up 0. So that is a charge of -5, so we'll call it Q-5. And we want to know the electrical potential energy associated with the arrangement. Well, if I look at my electrical potential energy equations, I've got two. One of them is when you have 2-point charges. So that equation is the electrical potential energy is equal to Coulomb's constant times charge 1 times charge 2 over the distance between the charges squared. I don't have an equation when there are 3 charges. What I have to do is I have to find the electrical potential energy between these two, then find the electrical potential energy between those two, and finally find the electrical between the last two. And then I need to add them all together. So we're going to go ahead and start. Let's find the electrical potential energy between the 4 nanocoulomb and the 6 nanocoulomb charge. So we've got Coulomb's constant, 8.99 times 10 to the 9th, times 4 times 10 to the -9th, times 6 times 10 to the -9th, all divided by the distance between the two, which was 15 centimeters, so 0.15. This distance is 0.15. The whole thing was 0.30. Type this into our calculator, and we get the electric potential energy to be 4 and 438 thousandths times 10 to the -6 joules. Step 1. Step 2. Find the electrical potential energy between another pair. So let's go between the 6 and the -5. Okay, well, the electrical potential energy between the 6 and the -5 is equal to Coulomb's constant times the first charge, 6 times 10 to the -9th, times the second charge, 5 times 10 to the -9th. Now, we do put the negatives in here because this is a scalar. It doesn't worry about the direction, it just tells us if it's increasing, decreasing. We do put the negatives in. Divided by the distance. Now the distance, this was 15, the whole thing's 30. Well, that must mean this is 15 centimeters as well. So divide by 1500ths of a meter, and we get the electrical potential energy to be -1.798 times 10 to the -6 joules. Okay, one more then. Let's find the electrical potential energy between the 4 and the -5 nanocoulomb charges. So again, Coulomb's constant times the first charge, 4 times 10 to the -9th, times the second charge, -5 times 10 to the -9th, divided by the distance between them, this time 30 centimeters, so 30 hundredths of a meter. And we get the electrical potential energy to be -5 and 99 hundredths times 10 to the -7th joules. Now, we want to find the net electrical potential energy. So we're going to add them all together. So 1.438 times 10 to the -6 plus -1.798 times 10 to the -6 plus negative 5.99 times 10 to the negative 7th. We add all those up. We get the net electrical potential energy to be negative 9 and 59 hundredths times 10 to the negative 7th joules.